For generations, Yellowstone National Park has been regarded as one of the most closely watched landscapes on Earth. Every tremor, every plume of steam, every subtle change in its colorful hot springs attracts global attention, because beneath its forests, rivers, and geothermal basins lies one of the world's largest active volcanic systems. News of any new crack, crater, or steaming vent inevitably ignites speculation about an impending catastrophe. That familiar cycle unfolded once again after scientists documented an unexpected transformation inside one of Yellowstone's most famous geothermal areas. Fresh fractures had appeared in the landscape, new vents were releasing steam, a newly formed boiling pool had erupted with surprising force. Images spread rapidly across the internet, accompanied by alarming claims that Yellowstone had begun to tear itself apart. The reality, while no less fascinating, tells a very different scientific tale. Researchers working in Yellowstone confirmed that the newly discovered fractures were not earthquake faults opening across the park. They were hydrothermal fractures created during an energetic steam explosion that dramatically reshaped part of Biscuit Basin on the morning of June 13th, 2026. Rather than signaling rising magma or the beginning of a volcanic eruption, the event reflected the immense pressure generated within Yellowstone's shallow hydrothermal system, where groundwater, heated by underlying magma, constantly circulates through a maze of cracks, fractures, and underground reservoirs. For scientists, the discovery represents an extraordinary opportunity to witness an active geothermal landscape evolving almost in real time. Biscuit Basin, located just north of Old Faithful along the Firehole River, has long been celebrated for its colorful hot springs, sapphire pools, and quietly steaming vents. Unlike the towering eruptions of nearby geysers, much of Biscuit Basin's activity has traditionally been subtle. Water gently circulated through mineral-rich pools while steam drifted through lodgepole pine forests. Visitors often viewed the area as one of Yellowstone's more tranquil geothermal destinations. That calm appearance changed within moments. During the hydrothermal explosion, immense pressure built beneath the shallow surface until confined water abruptly flashed into steam. Unlike liquid water, steam occupies vastly greater volume. The rapid expansion released tremendous mechanical energy, fracturing surrounding rock and blasting debris outward. Instead of molten lava forcing its way upward, the explosion was driven almost entirely by superheated groundwater trapped beneath relatively impermeable layers near the surface. Hydrothermal explosions have occurred throughout Yellowstone's history. They are among the park's most powerful non-volcanic hazards because they require no fresh magma intrusion to become dangerous. All that is necessary is heat, water, confinement, and a sudden reduction in pressure capable of converting liquid water into expanding steam almost instantaneously. When scientists returned to carefully document the aftermath, they found that the landscape had changed far more extensively than initially expected. One of the most striking discoveries was a newly formed hydrothermal fissure stretching approximately 61 feet, or about 18.5 meters, across the altered terrain. Instead of remaining dry like a tectonic crack produced during an earthquake, this fracture quickly filled with near-boiling water supplied directly from Yellowstone's geothermal plumbing system. The fissure effectively became a new hot spring almost immediately after forming. Its appearance immediately distinguished it from ordinary geological fractures. Earthquake faults generally develop through tectonic stress acting over large volumes of crust. Rocks slowly accumulate elastic strain until they rupture, allowing one side of a fault to slip relative to the other. Such movement often produces measurable displacement extending over considerable distances. The newly discovered Yellowstone fracture displayed none of these characteristics. Instead, researchers identified evidence that the rock had fractured outward from the tremendous pressure generated by rapidly expanding steam within shallow hydrothermal deposits. Rather than indicating movement along a regional fault system, the crack represented localized failure caused by internal fluid pressure. This distinction is critically important. Yellowstone sits atop a complex volcanic system, but it is equally famous for possessing the world's largest concentration of hydrothermal features. Thousands of geysers, fumaroles, mud pots, and hot springs exist because rainwater and snowmelt slowly seep downward through fractures until reaching rocks heated by magma several miles beneath the surface. The heated water then rises through intricate networks of fractures before emerging back at the surface. These underground pathways are constantly changing. Minerals dissolved within the hot water gradually precipitate along fracture walls, narrowing some conduits while opening others. Earthquakes too small for people to notice may subtly alter underground permeability. Seasonal groundwater recharge changes pressures within the system. Even gradual mineral deposition can redirect underground flow over time. Scientists frequently describe Yellowstone's hydrothermal plumbing as a living system because it continuously evolves. The June hydrothermal explosion appears to have dramatically accelerated those changes within Biscuit Basin. Field observations revealed not only the new water-filled fracture, but also multiple newly opened steam vents surrounding the blast area. Places where no visible geothermal activity had existed before were now releasing hot steam into the atmosphere. Elsewhere, older vents exhibited altered flow patterns, suggesting that underground pathways had been rerouted. Such changes provide important clues about conditions beneath the surface. Hydrothermal systems operate through interconnected networks of fractures resembling branching pipes. Blocking one pathway forces water toward another. Opening a fresh fracture may suddenly allow steam or boiling water to escape along an entirely new route. The June explosion likely reorganized this complex plumbing network almost instantaneously. Perhaps the most dramatic transformation involved the formation of an entirely new boiling crater. Scientists measured the collapse feature at roughly 21 feet by 17 feet, equivalent to approximately 6.4 by 5.2 meters. The crater, formed after the explosion, excavated shallow material while collapsing surrounding sediments into the newly created cavity. Water rapidly filled the depression, producing a vigorously boiling pool supplied directly by Yellowstone's geothermal system. Initially, the newly formed pool remained remarkably energetic. Observers documented intermittent bursts of water reaching approximately 20 to 30 feet into the air, or about 6 to 9 meters high. These were not true geyser eruptions driven by long-term cyclical pressure accumulation, but rather unstable surges resulting from the recently disturbed hydrothermal system seeking a new equilibrium. As underground pressures gradually stabilized, the vigorous spouting diminished. Today, the pool continues functioning as an active geothermal feature, although with behavior different from the dramatic activity witnessed immediately after its formation. To casual observers, these newly formed fractures, steaming vents, and boiling pools might appear to support fears that Yellowstone's volcanic system is becoming increasingly unstable. Scientific monitoring tells a different story. Yellowstone Volcano Observatory, which continuously monitors seismic activity, ground deformation, gas emissions, geothermal conditions, and satellite observations throughout the park, reports that the volcano remains at its normal background level of activity. Researchers have detected no evidence that fresh magma is rising toward the surface, no unusual patterns of volcanic earthquakes, and no significant deformation indicating pressurization of Yellowstone's magma reservoir. Instead, every available line of evidence points toward a localized hydrothermal event affecting only the shallow geothermal system beneath Biscuit Basin rather than the enormous volcanic engine that lies many miles deeper. That distinction forms the foundation for understanding why these newly discovered fractures are scientifically remarkable without representing evidence of an impending volcanic eruption. The challenge now facing researchers is determining exactly how the explosion reorganized Yellowstone's underground plumbing and what those changes reveal about one of the planet's most dynamic hydrothermal systems. Before the newly discovered fractures at Biscuit Basin captured worldwide attention, Yellowstone had already spent thousands of years demonstrating that its surface is anything but permanent. Across the national park, countless cracks, fissures, collapsed craters, and newly opened steam vents bear witness to a geothermal system that is continuously rebuilding itself. Some changes occur so slowly that only decades of photographs reveal the difference. Others happen in a matter of seconds, transforming familiar landscapes into entirely new geothermal features. The June 13th, 2026 hydrothermal explosion has now joined that long geological record, not as evidence of an awakening supervolcano, but as another chapter in Yellowstone's remarkably dynamic hydrothermal evolution. That distinction is essential because the word fracture often conjures images of tectonic faults splitting apart during powerful earthquakes. Scientists emphasize that the newly documented cracks at Biscuit Basin belong to a completely different category. These are hydrothermal fractures created when superheated groundwater abruptly flashed into steam, generating enough pressure to break apart the shallow ground. They formed within only the uppermost layers of Yellowstone's geothermal system and are unrelated to the deep volcanic plumbing or the regional fault systems that occasionally generate earthquakes throughout the Rocky Mountain region. Understanding why these fractures developed requires appreciating the extraordinary environment hidden beneath Yellowstone's colorful pools and steaming terraces. Rain and melting snow slowly seep into the ground every year, descending through countless natural fractures in volcanic rock. As this groundwater travels deeper, it encounters rocks heated by the enormous magma reservoir, lying several miles beneath the surface. Although the magma supplies the heat, it does not need to move upward for Yellowstone's geothermal features to remain active. Instead, the groundwater absorbs that heat before beginning its gradual journey back toward the surface. Along the way, the water enters a world of extreme pressure. Temperatures climb well beyond the normal boiling point, yet the water remains liquid because it is trapped beneath the weight of overlying rock and water. Scientists refer to this as superheated water. It stores enormous amounts of thermal energy while remaining deceptively stable until pressure changes. If the confining pressure suddenly decreases because of rock failure, erosion, shifting sediments, or the opening of a nearby fracture, portions of that liquid instantly transform into steam. The expansion is explosive. Steam occupies vastly more space than the liquid from which it formed. Within fractions of a second, expanding vapor can shatter surrounding rock, excavate craters, and blast mud, water, and mineral debris across the landscape. Unlike volcanic eruptions driven by molten rock and volcanic gases, hydrothermal explosions are powered primarily by rapidly expanding groundwater. Yellowstone has experienced this process repeatedly throughout its history. In fact, some of the park's largest craters were not created by lava or volcanic eruptions at all. They were carved by ancient hydrothermal explosions, far more powerful than the one witnessed during the summer of 2026. Features such as Mary Bay along Yellowstone Lake serve as reminders that hydrothermal explosions have occasionally excavated enormous depressions measuring hundreds or even thousands of feet across. Geological evidence indicates that those ancient events occurred long after Yellowstone's most recent lava flows, demonstrating that vigorous hydrothermal activity can continue independently of volcanic eruptions. Fortunately, the Biscuit Basin explosion was vastly smaller. Even so, it dramatically altered the local landscape. One of the most striking discoveries was the approximately 61-foot, or about 18.5-meter hydrothermal fissure that appeared where none had existed previously. Rather than remaining an empty crack, it quickly filled with near-boiling water supplied by Yellowstone's underground geothermal circulation. Scientists immediately recognized that this was evidence of a newly established pathway within the hydrothermal system rather than movement along an earthquake fault. Additional changes soon became apparent. Multiple new steam vents began releasing continuous plumes of vapor from areas that previously showed little or no visible geothermal activity. Nearby ground temperatures shifted. Existing hot springs displayed altered flow patterns. Perhaps most dramatic of all, a new boiling crater measuring roughly 21 by 17 feet, or approximately 6.4 by 5.2 meters, developed after the shallow surface collapsed. During its earliest days, the newly formed pool intermittently launched water approximately 20 to 30 feet, or about 6 to 9 meters, into the air before gradually settling into less energetic behavior. Although spectacular, these changes fit a pattern scientists have observed many times throughout Yellowstone. The park's hydrothermal features are constantly evolving because the underground plumbing that feeds them never remains fixed. One of the best-known examples occurred at Norris Geyser Basin, Yellowstone's hottest and most dynamic geothermal area. Over the decades, researchers have documented new fractures opening without warning, existing vents shutting down, and entirely new thermal features appearing after underground pathways shifted. Some springs that had flowed steadily for generations suddenly became inactive, while nearby ground that had once appeared ordinary began venting steam. The famous Steamboat Geyser provides another illustration of Yellowstone's constantly changing plumbing. For years it remained relatively quiet, producing only infrequent major eruptions. Then, beginning during the late 2010s, its eruption frequency increased dramatically, without any accompanying evidence that Yellowstone's volcanic system had become more active. Scientists concluded that changes within the shallow hydrothermal plumbing had altered pressure conditions feeding the geyser, rather than reflecting deeper magmatic unrest. Similar transformations have been documented elsewhere across the park. New hot springs have appeared unexpectedly after small hydrothermal disturbances. Existing pools have drained almost overnight as underground water found more efficient pathways elsewhere. Fragile sinter terraces built over centuries have fractured under the influence of boiling water circulating beneath them. Even earthquake swarms too small for visitors to notice have occasionally changed the behavior of nearby geothermal features by slightly modifying the permeability of shallow rock. These observations reveal an important characteristic of Yellowstone. Its hydrothermal system behaves much like a vast network of natural pipes extending through fractured volcanic rock. When one conduit becomes blocked by mineral deposits, pressure builds until water discovers another route. When a new fracture opens, steam immediately exploits the easier pathway. Closing one channel may increase activity somewhere else entirely. The visible geothermal landscape is therefore only a temporary expression of an underground circulation system that is continuously reorganizing itself. Scientists believe the June explosion temporarily accelerated that natural process. Instead of requiring decades of slow mineral deposition to redirect groundwater, the explosion fractured the shallow subsurface almost instantaneously. Water that had once traveled through older conduits suddenly gained access to newly opened fractures. Steam escaped through fresh vents. Heat became redistributed across portions of Biscuit Basin that previously exhibited different geothermal behavior. This reorganization of Yellowstone's shallow plumbing has become one of the most important scientific questions following the explosion. Researchers have returned repeatedly to Biscuit Basin using drones, thermal imaging cameras, precise satellite positioning instruments, laser scanners, and detailed geological mapping. Every survey helps reveal how the hydrothermal system continues adjusting after the event. Even subtle changes in surface temperature or water chemistry may indicate that underground circulation is still evolving. Water samples collected from the new pool and surrounding springs are especially valuable. The concentrations of dissolved silica, chloride, sulfate, and other naturally occurring minerals provide clues about the depths from which the geothermal fluids originated and the pathways they traveled before reaching the surface. If those chemical signatures change over time, scientists may be able to reconstruct how the explosion permanently altered the underground plumbing beneath Biscuit Basin. Meanwhile, Yellowstone Volcano Observatory continues monitoring the broader volcanic system through one of the most sophisticated volcano surveillance networks on Earth. Sensitive seismometers record even the smallest earthquakes. Continuous global positioning system receivers measure ground movement with astonishing precision. Satellite radar detects minute deformation across the caldera. Instruments monitor volcanic gases, stream temperatures, groundwater behavior, and dozens of other indicators capable of revealing changes occurring deep underground. The results remain reassuring. Despite the dramatic appearance of the new fractures, scientists have found no evidence that magma is rising toward the surface. Earthquake activity remains within Yellowstone's normal background range. Ground deformation continues to follow the gradual uplift and subsidence cycles documented over many decades. Gas emissions show no unusual increases associated with volcanic unrest. Those observations reinforce the central scientific conclusion emerging from the June event. The newly discovered fractures represent the immense power of Yellowstone's hydrothermal system rather than a volcano preparing to erupt. Far from signaling catastrophe, they offer researchers a rare opportunity to observe one of Earth's most active geothermal landscapes, reshaping itself almost in real time. Every new vent, every steaming fissure, and every altered hot spring provides another window into the hidden plumbing that channels heat from deep within the Yellowstone volcanic system to the surface. The landscape visitors see today is not fixed in stone. It is a living geothermal environment, continually sculpted by water, heat, pressure, and rock, with the Biscuit Basin explosion serving as one of the clearest modern demonstrations that Yellowstone is always changing, even while its volcano remains at normal background activity.